start the recording on this. So, okay. All right. So, Chapter 6. How many have heard of a line of best fit? How many have heard, for instance, a line, like if you have data points and you want to find a line of best fit through the data points? Okay, thank you. A lot of you have seen that. Thank you, Olivia, Benjamin, Peter, and hold on, and Catherine. Yes. So, well, you know that particular problem, a line of best fit, can be expressed as a linear algebra problem. Okay, a line of best fit through a set of data points is really a linear algebra problem. And what is a line of best fit? Well, it's a line that passes through a cluster of points, and the error between the line and the values of the points, the y values, is as small as possible. We try to minimize what's called the least squares error. Well, this is a linear algebra concept, or it can be thought of in terms of linear algebra. So in order to find, I mean, we really, one of the key ideas here is, suppose we have an inconsistent system of equations. An inconsistent system of equations has no actual solution. But there could be a solution that is like the closest, a best approximate solution. But in order to understand that, we need to understand what nearness means. Okay, what does nearness mean? Well, in section 6.1, we're going to learn about concepts of distance and orthogonality. And eventually, you're going to have a very good understanding of what nearness means. So I want to give you a little guided tour here of section 6.1, because I think the concepts are going to be pretty straightforward. So they start off by saying that geometric concepts of length, distance, perpendicularity are well known for r squared and r cubed, right? You learned about perpendicular, perpendicular line segments in trig and in geometry, right? Well, they can be generalized for n-dimensional space, and the concepts provide powerful geometric tools for solving many applied problems. Now, the first thing you're going to learn about is what's called the inner product. So the inner product is the same as the dot product. Okay, if you have two vectors, u and v, the inner product, let me blow that up a little bit here, the inner product of the vectors is defined as you take the components of each vector and multiply them together. Okay, so the first component of the first vector multiplies the first component of the second vector. The second component of the first vector multiplies the second component of the second vector, and so forth. And the dot product of vectors u and v would be u1 times v1 plus u2 times v2 all the way up to un times vn. How many have seen this idea, this concept of the dot product, perhaps in another class, or if you've taken multivariable calculus? How many have seen this idea of a dot product, how to compute a dot product? Okay, Eleanor's seen it, Catherine's seen it, very good, Hung's seen it, and of course now we're doing it, we're generalizing it to three-dimensional, or to n-dimensional space. These vectors live in n-dimensional space. So, okay, then let's go ahead and look at an example here. So in example 1, they want you to compute these two dot products, okay, for the vectors 2, the u vector is 2, -5, -1, and the v vector is 3, 2, and -3. So u dot v is the same as u transpose times v. You can think of it like that, right? And that is just going to equal -1. On the other hand, v dot u equals v transpose times u, and that also, incidentally, equals -1. Okay, so this basically shows that, I mean, it's clear based on the example that u dot v equals v dot u. It's called the commutativity of inner products, and inner products are commutative by virtue of the fact of the definition of the dot product. Okay, so if we go down here a little bit, they have a theorem, okay, regarding properties of dot products. Okay, so dot product is commutative. A dot product can be distributed. That's B. A dot product can be distributed, property B. If you have a constant times a vector u and you dot it with another vector v, the constant can be pulled out front. And property D, a dot product with itself, is always going to be greater than or equal to 0. Okay, are there any questions on theorem 1 on these properties? Okay, well, let's keep going. Let's keep going then. So the length of a vector, the length of a vector. Okay, so well, of course, I mean, you're used to, like in physics and like calculus 3, multivariable calculus, the length of a vector is, well, it's its length, right? It's its magnitude. Okay, and the length of a vector in terms of forces would represent the magnitude of a force if you have a force vector. Well, the length or norm of a vector, we can generalize that definition to be as you see here. Okay, and in fact, the norm of a vector is actually equal to the square root of a dot product. The norm of a vector v is the square root of the vector v dotted with itself. So pretty fundamental ideas here. Nothing fancy, nothing real fancy. Okay, and sometimes we want to have a unit vector. Okay, we want to have a unit vector. So for instance, in example 2, they say let the vector v be a vector with 4 components. It lives in 4-dimensional space. And components are 1, -2, 2, and 0. Find a unit vector in the same direction as the vector v. Well, okay, so we have to basically normalize. We call this normalization when we want to take a vector and create another vector with length 1. So what we do is, of course, we need to know the length of that vector v. So the norm of the vector v, or the length of the vector v, is found to be 3. And all we need to do then to normalize the vector v is just take the vector v and divide it by its length, or by its norm. Okay, that's all we need to do. And they do the process here. And so the vector u, that has length 1, has components 1/3, -2/3, 2/3, and 0. Okay, are there any questions on that? Okay. All right. Well, then let us continue here. Let us continue. Let's continue through here. Okay. So I'm picking various examples. Distance. Distance. Okay. So I think you know how to find the distance between two numbers. Okay. Well, the distance between two vectors is as follows. Well, they have an example. Actually, well, hold on. If you have, this makes sense. Hold on, let me move this up. If you have two vectors u and v, the distance between those vectors would just be the length of the vector u minus v. Okay, that's what it would be. Now, let me see here. One moment. One moment, class. Let me show you this graphically, okay? Let me show you this graphically. Let me bring up the whiteboard here. Okay, so I'm going to draw two vectors here. Okay, and let me label the vectors. This will be vector u. This will be vector v. Now, would you agree that this is the distance here in red between the vectors u and v? I mean, and I'll put like origin here, okay? And I'll put, you know, some dots here. The coordinates of the vectors. So we agree that that red distance there is the distance between vectors u and v. How many are comfortable with that? How many are comfortable? Okay, Eleanor's good. All right, all right. Well, so if we were to, hold on here now, one moment. Just trying to think about this. Okay, so this vector here, okay, I'll call that vector A. If we could find the length of vector A, or the norm of vector A, that would give us the distance between the vectors u and v. Okay, and let's see here. So if we were to redraw this picture, here, try to draw it best I can here. I want to draw it. There's the vector. No. Hold on. There's the vector u. Hold on, class. One moment. Hold on. what I'm trying to do is establish why the distance of vector A is equal to the difference between u and v, but the length, the length of u, the length of the difference between the vectors u and v. And let's see here. If we did this, hold on. Yeah, if we took the vector v and did this, what would this vector be here that I've drawn here? What would this vector in green be based on the picture? How would we label that? The green vector looks parallel. Ah, that's good, Nafani. That's what I want. That's right. This green vector here would be negative vector v. And do you see how then, no, come on, give me that line, give me that line. Do you see here how well A is just equal, by virtue of the fact of adding vectors, A is just equal to u plus negative v, right? So u, I mean, tip to tail addition. The vector, are you seeing this? That the vector A, based on the picture, this vector A. All I did was I took a vector A. Vectors are defined by their direction and magnitude. I just moved it over here, and it's clear that vector A, they're the same vector. This is the same vector, and you see that it equals the vector u plus negative v. I mean, is this okay? What I've written here, class? Good, good. Hong's comfortable, Eleanor's comfortable, and u plus negative v is the same as u minus v. So that's how that's geometrically shows you, it's an intuitive proof of why they come up with this definition for the distance between two vectors u and v. Okay? Are there any questions? Okay, well, let's keep going then. Let's keep going. Okay, so in example 4, compute the distance between two vectors. Okay, no problem. Just find the difference between the vectors, and then take the length of that difference, and you get the square root of 17. Okay. If you're good with that, let's keep going here. Okay. Then if you have two vectors, here's the distance between vectors u and v, and oh my goodness, distance formula, right? All right, no problem, no problem. Let's keep going if we're good. Now, orthogonal vectors, orthogonal vectors. This is very important. Okay, orthogonal vectors. So orthogonal vectors are vectors that are perpendicular to each other. Okay, orthogonal vectors are vectors that are perpendicular to each other. Okay, so let's just, all right, it turns out that two vectors are orthogonal to each other if the dot product of u and v equals 0. Okay, now they gave a little proof above why it's true, but I'll just give you a little example. Okay, so an example is sometimes worth 1,000 words. So let's say for instance, I'll draw two vectors here. Okay, hold on, let me draw. No, got to get used to this new thing here. So okay, here's an X, here's a Y. Okay, and I'm going to draw two vectors. Okay, this vector has coordinate 1, 1. Okay, we'll call this vector u. And vector v here has coordinate 1, negative 1. Are these two vectors u and v orthogonal? Are they perpendicular to each other? Clearly. Okay, that's right, Benjamin. I mean, we don't even need to, we just know it. We intuitively know it. We know what it means for two vectors to be perpendicular, and these two vectors are perpendicular. Now, if we do the dot product of u and v, notice now I have a nice solid dot for dot product. The dot product of u and v, okay, well, all right, the dot product of u and v is just going to be 1 times 1. Maybe I'll put this in red just to kind of put those coordinates in red. So I got 1 times 1, okay, plus 1 times negative 1. That equals 0. So now this is a little example to help you intuitively appreciate the fact that two vectors are orthogonal if the dot product equals 0. But this is true for vectors in n-dimensional space. I mean, it's a general definition. Okay. Are there any questions on that? All right, let's move on then. Let's move on. Okay. So there's a Pythagorean theorem, a general Pythagorean theorem for vectors u and v. And this should be, I mean, they have a little picture here on figure 6 to sort of help you to intuitively see it. We don't use that much in here, as I recall, but it's fine. It's fine. Good to know it. Now, orthogonal complements. Orthogonal complements. Okay, what's an orthogonal complement? What's that mean? Hold on, did I go too far here? Yep, sure did. Made the same mistake I always make. That's all right. Hold on, class. So remember, we talked about subspaces before. We talked about subspaces. Well, you can have subspaces that are perpendicular to each other. So what would it mean if a subspace is perpendicular to another subspace? Well, what that means is that the vectors in one subspace are perpendicular to the vectors in the other subspace. So we can call one subspace W, and we can call the perpendicular subspace, it's also known as the orthogonal complement. The orthogonal complement of W, or W perp, that's that W with the perpendicular sign there. W, I want to say it the right way. Hold on here. This is called W perp. W perp. Okay, and the definition here for W perp is the set of all vectors Z that are orthogonal to W, to subspace W, is called the orthogonal complement of W. And that's called W perp. And W perp is actually a subspace itself. Are there any questions on this? It's really just introductory ideas, introductory ideas that are talked about. Okay, let me stop the recording then.